This is the fourth part of lecture 6. In part 1, I had the introduction about wideband channel modeling. In part 2, I talked about GSM and JTC channel models as the basic traditional channel models which are used in wide area networks. In part 3, I talked about 802.11b and 802.11n channel models, which are a sort of similar to the GSM channel model, but I also expanded to Sale and Valenzuela's model, in which they were trying to model the arrival of the paths and amplitude of the paths. In particular, arrival of the paths, they are trying to model it as a Poisson process. And we said that this particular model is the foundation for 802.11n and also 802.15.3 models for MIMO and for ultra-wideband communications. In this fourth part of lecture, I will call it, let's say, advanced channel modeling. And in that part, I'm just going over those models for 802.11n and 802.15.3, a little bit of that. And then I talk about a lot of other advanced topics like frequency domain channel modeling, Raytracing algorithm, and also site-specific statistical models. But since we are short in time, we cover all of them just by descriptive words. We just describe that what has happened in them. So to start with, we start with it's our advanced channel modelings with path arrival. And up to now, and path amplitude based on the measurements. Up to now, what we had really, we were assuming that the paths are fixed in all our models until we talked about Sale Valenzuela's model. First, we want to show some stuff of measurements. These are the measurements which were done with Ganesh, one of my students, one of the early ones in indoor areas, which are trying to fit the arrival of the paths to basic Poisson. So what he does is he takes a bunch of channel impulse responses, he detects the arrival of the paths, and then he takes, for example, and divides them in bins, 5 nanosecond bins. Then he looks at the first 5 bins, or 10 bins, or 15 bins, or 20 bins, and for each of them, he calculates from the measurements and from the Poisson model the expected distributions. And these are the expected distributions using Poisson, the dashed line, and these are what he actually measures. And what he sees is that Poisson does not fit. And then he goes for 2 sets of measurements. These are 2 sets of measurements. Okay. Then what he does actually in the second one, he goes to adopt the so-called, maybe we have to change the position of the so-called modified Poisson process. Modified Poisson process, or delta K model, was a model that assumes that the paths are not independent. Means that if a path arrives now, there is a probability of lambda 1 that another path arrives after that, and there is a path probability of 1 minus lambda that after that no path arrives. And then after that the same story. Always you have 1 k times lambda, 1 minus k minus lambda. A path is there, a path is not there. And according to this now, when I go from in the, if you want to put this, fit this, for example, for Poisson, lambda is 0 really. I mean, each path is independent from the next path. In here there is a correlation, there is a probability, if I have a path, that I have another path after that, and is a probability that I don't have a path after that. And after the second one, then for the third, I have a factor k2 multiplied with the lambda, and this one is just 1 minus lambda, and then another k in there. So I have 2 parameters, k and lambda. Okay, and sometimes they call this delta K model because you have like two parameters. One is the delta, which is related somehow to the lambda, and the other one is the K that I'm using in here. This model also is referred to as Poisson process, a modified Poisson process. So you can call it modified Poisson or delta K model. This delta K model was examined as one possibility for 802.15.3. Okay. But if you use that Poisson, modified Poisson model, these are the result of Ganesh's work. They fit very well with the measurements. Actually, you can adjust the K and lambda so that modified Poisson model fits the result of measurements. So if you want, this is the result from Poisson for fitting in 5 or 10 or 15 or 20 bins, and these are the results if you use modified Poisson. Measurements versus calculations. So basically, that's one line of work. The early work in here was done with the students of Turin in 70s for the urban areas. For the indoor areas, this is the Ganesh who does this one first, and it gets applied for the indoor, or it gets examined in 802.15.3. So this is one of those advanced areas in channel modeling. Now, the other issue is, now this was the issue of arrival. Okay, so Poisson arrival is not correct, and that was the conclusion that we got by examining, like for the NSF, we did that to examine Saleh and Valenzuela's work. And we showed that arrival is not Poisson, it's modified Poisson. Okay, the second issue was that in Saleh Valenzuela model, arrivals are assumed to be what? Rayleigh. So what again Ganesh did, he took like channel impulse responses, they got all the paths in one bin. So you get the channel impulse response like this. You divide it into bins. Each of these bins are 5 nanoseconds because the bandwidth is 200 megahertz. And what he does is that he comes in this bin, either I have a path or I don't have a path. If I have a path, this path has certain amplitude. Okay? Then I get all of these amplitudes and I fit them to density functions. See, Saleh was not doing that. They were making this assumption, they are Rayleigh. And when they do it, then to fit it with the curves, they come up to things like this. If we come back with the computer, we see that. Now, these are like cumulative distribution function of different distribution functions. This particular one is Rayleigh. This one is the measurement. This one is the measurement. And then this is log normal. Okay, so you can see now that these are several. This is log normal, Nakagami, Rayleigh, Suzuki, and Weibull. All of these functions were derived with Turin's students actually, but Ganesh took all of them and applied it to the indoor channel measurement. And the conclusion is that number one, Rayleigh definitely doesn't fit. Number two is that basically log normal fits. At that time, we had difficulties to explain that, but now that the time has passed by, we know that because these measurements are with very wide bands, like 200 megahertz. But at that time, nobody was even curious about 200 megahertz bandwidth. Bandwidths of measurements that like Ted Rappaport was doing was at most like 40 megahertz, something like that. We were using the widest bandwidth, but 200 megahertz is important for who? For ultra-wideband type of application. Okay, because they have a minimum of like 500 megahertz. And when you go above like a couple of hundred megahertz, behavior looks like ultra-wideband. You have many, many paths. And then as a result, paths, they don't combine with one another. So you don't have variation in Rayleigh fading. Okay, so that was, and since that's the case, they don't fit the Rayleigh anymore. And what do they fit? They fit the log normal, best and everything. Why? Because log normal is shadow fading. And if I have, see, the channel in frequency domain is something like that. Okay? If I have a bandwidth like this, this is Rayleigh. But if I get a bandwidth like this, I'm averaging the fading, Rayleigh fading. It's no more Rayleigh anymore. What is that? It's shadow fading. What is the statistics of shadow fading? Is log normal. And this is something like very advanced today, actually. Because the models for ultra-wideband, all of them, they assume that each path is log normal. And arrivals are not Poisson, or either delta K or modified Poisson, or they have other solutions for that. Okay? So this is one point. Okay? Now, Ganesh also tried to like fit the measurements with like those exponential. Do you remember that? Like I had exponential decays. Exponential decays that like Saleh was talking about. Okay, he did, and he find the experimental value of exponential decays. But we had very difficult time to find a lot of more than one clusters. Most of our measurements were one cluster. Okay, but still double cluster model is very good, and people are using that. But when you do time domain measurements, these clusters, they come on top of one another. It's very difficult to see which is which, to differentiate them from one another. Then later on, I will show you there is one technique to at least differentiate clusters. But with time domain measurements, very difficult, and Saleh and Valenzuela has jumped to a conclusion very quickly on that. You can't take it from time domain measurements that easily. But anyways, this is like, that's a standard deviation, and this is the mean of the measurements, and this is the total power. This is actually the delay power spectrum. And always in here you have, these are measurements, these are the best fits. It gives you some idea about like this exponential decay exists. It's a reality. Exponential in what? Arrival of the received power or delay power spectrum, which validates what we have in 802.11b model, for example. These things are supporting that. Okay? Delay power spectrum, which you want, if you want to measure delay power spectrum, what you do? You evaluate the power received at different delays in different locations, and always you end up with exponential, which is consistent with what we have in 802.11b model. But this is TAR-MS done for, so one of the methods to fit the result of measurements with like wideband models is that you do the CDF or complementary CDF. These are actually complementary CDF of measurements and the models. In here, we have, these are done again by Ganesh, two models. One is Poisson-Rayleigh model, which is very similar to what? To Saleh-Valenzuela model. And then the other one is modified Poisson and log normal distribution, which is similar to what students of Turin originally observed from outside and Ganesh observed for indoor. And these are empirical data. What you see is empirical data is very close in two areas. Two modified Poisson log normal, and they are not as close with Saleh-Valenzuela's model. Okay, so delay power spectrum fits better with modified Poisson and log normal if you extract the numbers from the actual measurements. This is one of the conclusions. Okay. So that's what I wanted to talk about in terms of modeling of path arrival and amplitude. And basically what I told you was that path arrivals, the way that is modeled as Poisson, and path amplitude as Rayleigh is not valid, doesn't fit with the measurements if the measurement bandwidth is above several hundred megahertz. The first observation was Ganesh's observation that I showed you those results. Based on that, ultra-wideband model was developed, which we will discuss that actually later on not in this lecture, when I talk about ultra-wideband. But basic of that is very simple. What they say is that arrival of the path is not fixed, is random, and it's not Poisson. Is modified Poisson or something replacing modified Poisson. And then the other thing that they say, the amplitudes are not Rayleigh anymore. They are what? They are log normal. This is substantial difference with any other models that we have seen in any other standard. And the reason is the thing that I told you. They are average. If bandwidth is too much, you're averaging over fading. Okay. Then the next one is simulation of angle of arrival. Why are we interested in simulation of angle of arrival? I told you, because of MIMO. Earlier I told you Spencer did a measurement system to measure the angle of arrival, and based on his measurements, he started to develop some models. Another early measurements of angle of arrival was Bob Tingley's measurement system, which was done again around, both of them, Spencer and him, they did around the year 2000, but Spencer also developed a model for the angle of arrival. The model is quite simple. He takes that concept of clustering. He says, since these paths are arriving in clusters, so there is like a mean value for a cluster, for angle of arrival. So a cluster actually arrives from one angle, okay? And then when it's arriving from this angle, then inside this angle, this is the mean of the angle. This mean is like uniformly distributed, for example, or you can divide it, whatever. Okay, but around this mean, it has a Laplacian distribution like this. This is the Laplacian distribution. So I have one cluster like this. Angle of each of points in here has a mean, which is this one, which is this capital phi, and then it has some small values on top of that, which are coming from a random variable, which is Laplacian. Does it make sense? So then, what he's really saying is that from each angle, I have clusters. Clusters are arriving from different angles, but from each angle, they have a Laplacian. A little bit changes around the angle. This is a Spencer's model. Very valuable model because it got adopted in 82.11n, a modified version of that. Okay. Now, so what is that modified version that they have used in 82.11n? In 82.11n, what they have done is they again assume that these things are, multipath components have fixed distance between them. But they arrive in clusters. This is cluster 1, this is cluster 2, this is cluster 3. Okay? Within the clusters now, you assign angle of arrival according to what? Each of them, they have different one according to Spencer's model. This is the MIMO model. Okay? So now, when I look at these clusters, I have different angles. I can go three-dimensional now. Okay? One of them, it's three-dimensional. Now, because associated to each path, now I have what? An angle of arrival as well as like delay of arrival. This is the delay of arrival. Angle of arrival, they calculate it from what? Spencer's model. Which means that they have a mean within the cluster, and within the cluster they have Laplacian transfer, Laplacian distribution. Okay, so if the mean of this guy is like 10 degrees, around the 10 degrees, I go to this Laplacian random variable, I generate like one value, and I add to that mean or subtract from that mean, and that would be my associated phase to that. And all of these guys, they have the same means. These guys the same means, these guys the same mean, these guys the same. Make sense? What is good about it, now I can use it for what? MIMO. For performance evaluation of MIMO systems. Because they need the angle of arrival. Now, this is like the delay power spectrum. We have talked about that. I mean, in 802.11, they are using like this function for delay power spectrum. Okay? Which is like a bell shape or like a low-pass filter shape. It's easy to implement, and it's consistent with what? With like measurements that Steve, for example, had done, and I had shown you earlier. So that was about like simulation of angle of arrival for MIMO and simulation for ultra-wideband. I talked a little bit about that. What else? There was another frequency domain model that Steve Howard originally introduced it. Some people more recently, they applied that to ultra-wideband type of communications. And basically in this model is that when you look at the frequency domain, this looks like a speech actually signal. It's a random signal in there. And if you go with the spectral estimation techniques, you can model that in very similar to frequency domain measurement system, really. So you can model this to be the output of a filter in frequency domain, which is run with Gaussian noise, and then define the parameters of this filter, which is location of the poles of the filter. This is called, in a spectral estimation, parametric spectral estimation. Means that rather than, I want to model this, for example, in frequency domain, I model this with a Gaussian noise running a filter, and filter has 2 poles only. So I have 2 parameters to model the entire thing. If I want to model in time domain, I have a bunch of paths, a number of paths, many parameters that I have to model. Okay? But in here I have very limited models. This is one model. I think these are the detail of that. These are fitting of Steve's model to like poles. He has like, these are 2 poles close to the unit circle, 3 poles in the center, which are not important. I can neglect those and keep only these 2. Okay, if I keep, these are result of measurements. Okay, doing the, so he takes a bunch of frequency domain models, and he does like 5 pole, he determines 5 location of poles for the filter. And these are the 5 locations of the poles for different measurements. 2 of these poles are dominant all the time. The rest are redundant. And these 2 poles are associated actually to 2 clusters. And this is the only way that I have seen to show the cluster arrival. I think the way that Sullivan and Suella were showing cluster arrival, it was just off the air. It was made up imagination. Steve was the first person who could show the clusters. Okay, arrival of the clusters. So what does it mean? If you take a measurement like that in time domain, okay, if you have 2 poles, frequency response, time response actually in here, time and frequency, this is the response that you expect for 2 poles. So this is one cluster, this is another cluster. So you see 2 clusters in them. But if you go to, we couldn't clusterize these things any other way. We couldn't see it. So it was assumption. So one of the advantages of this frequency domain modeling is to put them in clusters. So in reality, what Steve has shown is that we have 5 clusters, but really 3 clusters, are not useful. And there are 2 dominant clusters that we can detect. Okay, so these are like a little bit more advanced modeling. These are result of how his models fit the measurements. This is in terms of delay power spectrum from the measurements and from the models that he has developed. And they show very well fit for the RMS delay spread. And these are more details of that type of thing. So this is like frequency domain modeling that I wanted to talk about. Now, if you want to compare frequency domain with time domain modeling, frequency domain modeling is much more simpler. It just uses two complex numbers to represent, and then you have to give the statistics part of those poles, because the location of the poles are changing from one to another channel measurement. Okay? But the problem that people criticize with frequency domain modeling is that it's very mathematical. See, time domain modeling, you associate arrival of the paths to the physics. In here, that physics is missing. The only physics which exists in there is association of the poles to clusters. So people have looked into that, and people have done other things as well. In 802.15, I believe they also looked in the frequency domain model as well. But finally, they resorted to time domain. So these are, and that's actually, frequency domain modeling is the advanced modeling for the so-called statistical modeling, measurement-based modeling. And so in measurement-based modeling, we have time domain and frequency domain. The most popular today is the time domain modeling. But frequency domain modeling is something very new, and a couple of people have been attracted to that. Now, other modeling, advanced modeling, one is using ray tracing algorithms. We saw the ray tracing algorithms earlier. Actually, we did some homework based on ray tracing, but we had only 1 or 2 rays. But you can write software programs which are much more complicated. So for the ray tracing, well, you have ray shooting and mirroring, 2 techniques. You used mirroring so far, but ray shooting is that I stay in one location and I send a cone in different locations and I turn it. So I can write the software by changing the angle, and any time that the cone hits a wall, it gets reflected, and also another component goes through. You can write the program for that. Okay? Or you can do mirroring, like what we did actually in our 2-path and 3-path ray tracing models that we studied in chapter 3. Means that you find the image of the sky, and then you connect the image to the receive point. And from that, so do you remember that? If I want, for example, if my receiver is in here, transmitter is in here, I find the image of this, and then I connect these two. So this is my path, which goes from here to here. Again, you can automate that too. Okay. Now, there are 2, and this is the 2 techniques. These are some results of ray tracing. You have also a video on the lab experiments, which is like you can play with the ray tracing with that and learn a little bit about ray tracing. Using ray tracing, you have a number of paths. You can find the impulse response, and based on that, for example, in here you have find the coverage. Means the total power received in different points, and these are different levels of power, different colors. Equations that you need, one is for reflection, one is for transmission, one is for diffraction. These are the most important phenomena. Detail of that is inside the book, but is beyond the scope of this course. These are different ways in handling those values. This one shows how close ray tracing is to the result of measurements. It's very, very close to the result of measurements, actually, for the power in the indoor areas. These are, again, result of ray tracing compared with finite difference time domain. Do you remember what was finite difference time domain? That was direct calculation of Maxwell's equation. So you divide the building into like grid, and the grid should be the length of what? Lambda. Fractions of lambda. So here we are. That's huge computation. But if you just make some approximation, you can use it. We tried it actually. We were one of the early people who did finite difference time domain. Professor Jim Fahlin here was actually very, very specialized in this field. He did a project for our laboratory, one of the early projects in finite difference time domain. And the trick that he did, he reduced the frequency of operation from 1 gigahertz to 100 megahertz. So now you have longer grids. Results are comparable with ray tracing, but ray tracing is easier and more convincing. These are some results of ray tracing outdoor. done by Ganing Yang, one of my PhD students, for the 9X mobile, which is now Verizon Wireless. There are 4 blocks of building inside the Manhattan, and Verizon did a bunch of measurements, and then Ganing did like ray tracing software, which has a lot of diffraction to fit those measurements. And this is like some result. I mean, you take that and put it on top of the building. Result of propagation. Receive signal strength using ray tracing. This is, again, these are those buildings that we talked about, blocks of building that we see in here in 3D. And these are result of measurements, how close they are to ray tracing. Ray tracing provides very good result. But in the outdoor, it needs a lot of hand pick of the locations that you diffract. So implementation is very difficult. For indoor, it's easy and good. Now, this is another like ray tracing sample. These are path loss, and again, results of ray tracing in variety of different scenarios. Ray tracing is very good for getting, like creating these color charts for whatever you want, a strength of the first path, or line of sight for obstructed lines, so whatever you want to do. If you want to get the individual paths and analyze that, ray tracing is very useful. But ray tracing has one major weakness. The major weakness is that it provides just static channel models. Doesn't simulate variation of the channel because you are not in ray tracing implementing all the details. And one of those details are people who are moving around. But still it's very good for the research type of thing. The last type of, so ray tracing is right now used actually, many of my students use ray tracing for modeling, for understanding of the channel. For example, for analysis of time of arrival of the path, for modeling of the time of arrival of the first path. Ray tracing was very useful actually for understanding the phenomenon, what is going on. The same, it can be used for angle of arrival. Is very good for that type of thing. But as I said, it doesn't have variations. So to put variation, you can take the channel impulse response and add random phase to each path which arrives. That's equivalent to effect of movements of people. One of my PhD students actually did that for his part of work. So the last item of these advanced modeling techniques is the so-called site-specific statistical model. See, I talked about 2 types of models. One is site-specific, like ray tracing, which is very accurate. The other ones are measurement-based statistical models, which I have to go to a lot of buildings. It's an engineering solution, really. But the good part of a statistical model is that when I developed it, it's easy to implement. I mean, universally, everybody writes 2 lines of code and does it. Okay, but it doesn't relate to the physics of the building. So another thing is that can we combine ray tracing with a statistical modeling? That's actually the latest thing. One of my PhD students, Maud, did that for his PhD, and some of the students of Ted Rappaport did things similar to that. And basically what you do is that you come to a building, you say that if I have a building like that, I have transmitter and receiver, I can statistically tell you that based on density of number of walls, how many walls are in between, and what would be the arrival rate. Statistically, you can do that. Okay. What you say is that my coverage is like so much, so if I get like an ellipse around here, if I take an ellipse around here, okay, ellipse, if you remember, has a function that this thing plus this thing is constant. Is like L, okay? And this is like a path. If the path loss associated to this is like 30 dB, I can sketch like an ellipse around this as the area that I stay in it, okay? And then based on that, based on density of the walls, I can develop some model, statistical models. So then somebody comes and says, this is density of my walls. These are the type of walls that I have. Okay? Then you develop like your delay power spectrum for him. And this is what that mod did actually. These are some delay power spectrums actually. And he fit those things with the result of ray tracing, and they fit very well, these statistical models. And I have other PhD students currently working on that. These are other, in fact, fittings of measurements based on. So basically what you do in the statistical models, building a specific statistical model, you come to a building, you say what is density of walls? So I get the whole map, I count the number of walls, I divide them together, and that's the density of my walls. And then what is the material which makes the walls? You can do that. Based on that, you come up and you develop a model which evaluates the delay power spectrum. Very, very nice way, very physical. This is something that I think is the trend for the next step of channel modeling for like indoor areas. It's better than that 802.11b. See, 802.11b, I liked it because it was one equation covering everything. This is also like that, in a sense. And also it's good for modeling of new phenomena like this, like time of arrival modeling or angle of arrival modeling, if you want to do and relate it to physics. With that, I think I want to finish the last part of lecture 6. Do you have any questions? If you don't have any questions, next week we will have the exam, and our next official lecture would be lecture 7, which is Introduction to Modem Design Technology and how we use the channel models for performance evaluation of the modems.